Yeah, when you think messaging, right, there's a couple of things, right? You think like maybe the first thing is maybe like transport, right? What's a transport mechanism? So this could be uh, you might use like say like shared memory, right? Or you might use like a socket, right? Or you might use like a pipe, right? Um, you might well, you might layer on top of some other IPC, right? Um, so the first thing is like what's going to be your transport, and each of these have their advantages and disadvantages, right? Um, uh, Now, yeah, for example, like if you just have a shared memory, and you can either manage this, like you can have the kernel manage this, like through some existing IPC mechanism. You can set up your own shared memory. You can allocate your own shared memory area using a map or something. So this might be fast and easy, but then you have other problems like let's say you put pointers in a shared memory, and then some other process comes in and reads those pointers, and it's all wrong, right? So uh, you might use a pipe. It has also got some niceties that come with that the kernel provides, but then you have other issues, right? Like there's like buffer size limitations and other stuff like that. You can use sockets. Again, that's a nice interface the kernel provides. But then you gotta figure out things like bind and all of that, right? Uh, so yeah, the first thing is probably like the transport itself. Like, what transport are you going to choose? Um, okay, the second thing, I guess, after you figure out the transport is probably the wire protocol, right? Or the wire format. Like what's going to go inside an IPC message, right? So, this could be like a TLV. Um, this could just be like a raw buffer. Um, um, this could be like, you got to implement things like I mentioned before, like encryption or compression or whatever, right? Um, So that's probably so that's the next thing. Like, what's a wire format look like? And depending on the wire format, right? Like, it will incur different levels of overhead, right? Like if you use say like a raw buffer, like you don't have that much processing time, right? Like maybe you just index into a struct, right? But if you use something like encryption and compression, now you have a lot of overhead, right? On a like getting the data out. So um, uh, and that will impact things like serialization overhead, right? Uh, so I would say that's the next thing, probably like the wire format. Uh, Probably the third thing is going to be maybe like the data structures. And this will be something like, do you use a queue? Do you use like um, like you can think like um, multiple buffer pools, right? Like use like buffer pools. If we do use a queue, what type of queue do you use, right? Do you use like a parity queue? This might be useful if you need to order by timestamps, or do you use like some type of lockless queue, right? If you want to support some degree of concurrency quickly. So, some, other things is like if you need some type of ordering, maybe you need like a try or something like that, So, yeah, depending on like what the IPC mechanism is, and what sort of the guarantees made by that, you have to choose like the right data structure to sort of represent the actual internal thing, right? that would probably be the next thing. After that would be like maybe like I guess maybe like the broker design, or maybe, oh yeah, see, this is another complication. Like, do you even have a broker, right? So what I mean by broker is something like is essentially a daemon whose responsibility is to handle the messaging things. And this could be something like routing, flow control, retransmit, reliability, right? And the typical architecture would look something like you have something like a broker, and then you have like a producer, consumer, and the broker would handle. The broker would basically own all of this logic, so the producer and the consumer don't have to re-implement it. But if you do have a broker, now you have extra work to do, right? Like somebody has to implement this thing, somebody has to, and there's some performance overhead with having like a whole separate daemon whose job is just to be a broker, right? But you get a lot of niceties by having a broker, right? So yeah, so the next thing I probably would think about is like, do I have a broker? Like, and if I do have a broker, it's gonna implement some of these data structures and all of that, right? So, that's probably the next thing I would say. After that, likely maybe interfaces. Yeah, that's probably a good one. So this is gonna be like like what like not only is it going to be like what if you have like read, write, like some of the things we discussed before, like you do provide a batching mechanism, that sort of thing. Yeah, so it's going to be that, but it's also going to be like interfaces with like other things, like do you provide like a REST API, right? And if you do provide a REST API, is it layered on top of like, say, this, right? Or do you have like a proxy, right? Or other thing is like, do you have schema, right? Now, this can make a big change, right? Because if you do have, if your IPCs do have to follow a certain, if your messages do have to follow a certain schema, right? Like what data structure you use over here, then will be like, it will change, right? Like maybe you can provide better guarantees if your messages have to follow a certain schema, or that type of thing, right? So, so yeah, interfaces I think are the next thing. Yeah, and then the last thing is probably like maybe like patterns, I guess. Like what does your IPC mechanism enable, right? So this could be like, do you do something like request response? Do you provide maybe like a pub sub type interface, right? As well as some of the reliability patterns that maybe you'd want to layer on top of some of these. Yeah. So I know that's a little broad, but I think that that's probably the right place to start, like in terms of just broad overview. Like when you're approaching something like a generic question, like give me an IPC mechanism, right? Like if you kind of think about it, I sort of went up the stack, right? Like I started with the bits and the bytes of transport, and then I worked my way all the way up to the application patterns, right? And then now after we've done that, next thing to do is, okay, what do you think you want to focus on? And then let the interviewer kind of guide, like, okay, maybe and different interviewers will have different things that they think that they're interested in. Like maybe some of them will be like, let's talk about this broker design, and then you have some fun things you can talk about with routing, flow control, service discovery, whatever, right? or maybe some interviewers are more interested in data structures. So now you can talk about like priority queues or something, right? Some of them are really into serialization. So you talk about how protobufs are the best thing ever since Google invented it. So does it make sense?
Hey, nice. A quick question. So, with respect to the transport, right? So, you mentioned the different mechanisms like shared memory, pipe, sockets, etc. So, could you do maybe like a quick trade-off analysis on which one would be better suited for which scenario?
Yeah, sure. So you got a couple of things on Linux, right? Or maybe like Unix in general. Let me try to remember off the top of my head what you got going.
No, I think whatever you listed, right? Can you hear me?
Yeah, I hear you, Sebastian.
Hey, no, I think whatever you had listed, like shared memory, socket pipe, I think that probably covers all the Unix IPCs. There is one more which is message queue. Yeah. I think those are, and I mean they bucketize semaphore and signals as IPC mechanism as well on Unix, but I think it's not really an IPC mechanism in that sense. It is, but I mean it's not like a message passing thing, right? So, yeah.
Yeah. Yeah. No. But yeah, let's maybe like talk about the different transport mechanism, right? Like why what is what and why you would use what. Yeah. Okay. So yeah, you got shared memory. This is the most basic thing you got. It's literally if you have process 1, process 2, the kernel will sort of open up some scratchpad memory over here, right? And each of these guys basically just read and write to this like individual place in the kernel mem. That's the most basic one. Now,
but the shared memory doesn't need a kernel transition, right? It just sits in and the both process has the mapping to the shared memory, so they can just communicate between the processes without requiring a kernel transition to write or read to the buffer, right?
Right. Yeah. Like
yeah.
I mean, like what the idea is that it's mapped over in the user space. When I mean kernel is like it's you've mapped the kernel, the memory, the physical memory, I guess maybe that's a good way to put it. You've mapped it to something sitting in the user space, and then you can just blast whatever you want to. It's that shared memory area.
Yeah. Makes sense.
Yeah. Mm-hmm. So advantages, speed, right? You don't have a lot going on over here. Like really the kernel is basically. I mean the mechanism is just like we've given you memory. You can do whatever you want with it. So speed, flexibility. Maybe like simplicity. Like it's pretty easy to just go ahead and use this what the kernel has provided. So now the downside is like you have to do everything yourself, right? So with all this nice stuff, now you're in the position of having to do all the yucky stuff, right? So like size management, maybe I'm gonna call it like size management, usage, flow control, like whatever, like like the application has to sort of like manage all of that. and you know, like it's, and you need to set up like synchronization, you know, like you don't want both processes just write in the same memory area. So you know, people will have patterns where like they'll have the shared memory and then they will sort of like split it. And the top half will be maybe for P1 and the bottom half will be maybe for P2, right? And then you know, they'll maybe use some type of semaphore between the two, right, to do like a signal, right? And they could say something like, okay, I'm done writing to P1, I'm done writing to my scratch pad, go ahead and read it or whatever, right? So, but the thing is you have to do it all yourself. So it's kind of a pain, right? Yeah, so that's sort of shared memory. That's Bhargavi, does that make sense?
Yeah, Moise.
Yeah. Now we can maybe talk about pipe. This is, again, kernel will kind of do the same thing. Like you can imagine you have P1, P2, and then you'll have some portion of the memory that the kernel allocates, and this is going to be what's used to send messages through like a pipe. So now you're not exposed to this. All you're exposed to is the pipe interface, right? So that's the first thing. Yeah, there's like a pipe interface, you know, I'm not really sure how much I want to go into pipes because I feel like almost everyone has used pipes before, right? But you know, there's things about it. Like for example, like it's explicitly blocking, right? So if you wanna, if you want unblock, you have to manually set it, right? I'm not really quite sure what else to think about. Maybe
have to, like, I don't not looking for the how they work, just more like which one might be suited better for which type of IPC application, like design considerations type of thing in terms of using the transport.
Got it. Okay, yeah, sure. No, sounds good. Yeah, so then if you look at your kind of the 4 or so mechanisms that are provided, right? Shared memory, you want speed, flexibility, but you manage everything yourself. So, you know, if you like, this will probably kind of be the building block, right? If you want to write your own mechanism to do whatever, and it'll do whatever you want, you probably internally, you're going to be implementing it with some shared memory, right? So I'm going to say build yourself. That's a shared mem. Now, if you want something deterministic, like it guarantees messages, gets on the other side. Like if you want, like, I'm going to say like a mini broker, right? Yeah, now you can use something like pipes. So, you know, like I said over here, you know, broker does a lot of things for you. If you just need, if you need like a small subset of the use cases, pipes cover like a big chunk of those. So what I would call like a mini broker. Pipes are a good mechanism for that. Message queue is going to be like, maybe if you want a little more functionality, right? Maybe like pipes plus. Message queue will be a good use case for you because you can map individual queues to individual priorities and a couple other things. And it provides a lot of the same niceties that pipes provide. So, and you know, this is useful for things like, say like logging, right? Like if you need like different priority levels or you want to log by like timestamp or something like that, right? So, yeah, so message queue will sort of be something on top of that, right? Now, if you want something like why would you use sockets? Well, if you want API compatibility, maybe also like unknown destination, and like general abstraction, right? Sockets will be good for this. So now, why is socket? What do I mean by this? Basically, like, you know, if you're sending a packet to like a certain address that you've bound to, that address could be like something sitting on the same CPU core. It could be sitting like in a peripheral device. It could be sitting, you know, somewhere way over there in the network, right? So if you want a more like general RPC mechanism, not just IPC, right? Socket will probably be the right thing to implement there, right? And then like what would happen is that some of these considerations, you can even move it to other parts of the system. Like, you know, you could have the broker running on a completely separate node or a completely separate core and just dedicate it to doing the broker stuff. So sockets would kind of provide you with a more generic flow control and a generic API layer. But then the downside is that, you know, sockets they're very specific, right? You have to use them like with all the BSD APIs and all the stuff that comes with that. So whereas something like shared memory or pipes or whatever, like generally the interface is very simple. So does that make sense? Does that kind of cover the basic use cases?
Yeah, I think it's clear. Thank you.
Mm-hmm. Yeah, so now if you kind of like in the real world, if you think about it, like common IPC things, right? Like if you use, I don't know, maybe like 0MQ, right? 0MQ internally is implemented using sockets, right? Because it's providing you that abstraction and flexibility, right? So I have seen many more generic IPC frameworks use sockets. Like protobufs, you know, it will use HTTP2. 0MQ uses BSC sockets. Oh yeah, you know, that's another. I guess that's another thing. You can go full. You know, this is. Hopefully you don't see this in the embedded context, but you know, nowadays people do all sorts of things. Some people just use straight up REST APIs, like HTTP REST APIs, right? And they have like a web server sitting on the device itself. And why would you want to do that? Well, it's really easy. Like all the tooling and APIs is available for you. But the trade-off is a big performance hit with everything to do with REST, right? Like, you know, parsing JSONs and HTTP and setting up a web server and all that yucky stuff. So other thing I think I've seen people do, which is, again, I don't know if you really want to do this, but you can use like a local DB, right? So this might be like, say, SQLite. And then, you know, they just treat the local DB as sort of like the transport, or the backing store. So, you know, you would just, you can implement like pub/sub pattern or, you know what, and you have the DB handle all the yucky stuff with serialization and parsing, validation of messages and all of that stuff. Yeah, but these two things, yes, people do them. I would maybe make reference to it in an interview context, but would I kind of go down this rabbit hole? Then the answer is no. Kind of for obvious reasons. So, any questions on this?
I think that's good. So the socket is kind of, I mean the pipes or the shared memory or the message queue is mostly local processes on the same system are communicating. But with socket, you could communicate with not just the processes on your system, but you could talk to processes on the other systems, right?
Yeah, exactly. Because socket is just a generic. It's going to be like an endpoint, right? Not necessarily a file descriptor or something. So you have some more flexibility, basically. Like you can write, you can move from just an IPC mechanism to a RPC mechanism as well. So.
Right. Okay. And I think, I mean, the way you broke it down to different aspect, I think it was very helpful. The broker aspect is, yeah, I mean, if you look at shared memory versus pipes or message queue, I think in the shared memory there is really no broker there, right? I mean, in the pipes and on message queue, your kernel is working as a broker for you, right?
Yep, exactly. That's why I like to think of it like as a mini broker. Like the kernel is to give you some guarantee, like the message will get to the other side, or it'll fall in a certain queue, or the contract for the service discovery, the endpoint discovery is file descriptors, right? So they're sort of like a lightweight broker mechanism. But you can think if you need like a more robust mechanism, like you will probably need to write your own broker. And then the broker will have the things that, like I said, it's the things that come with it, like the routing and like how do you make it reliable, and how do you do retransmits and blah blah blah. So.
Right. Okay. Yeah. And I think what you mentioned is like there is bigger context to IPC, right? Rather than just those Unix IPC mechanisms, right?
Exactly. Mm-hmm.
Yeah. You could have your own, other than those standard Unix IPCs, you could design your own IPC mechanisms. Okay.
Exactly. Yeah, and I mean, in the real world, like, unless you need something really small, like basically, I've only really seen two things, right? I've seen, shared memory, which is like I described. Usually two processes, they're blasting some scratch pad. And then they signal each other like, okay, you can read my memory now, right? That's the first pattern I've seen. The second pattern I've seen is like you bring in the whole broker, like you set up 0MQ or RabbitMQ or something, right? And then you do all the fun stuff there, but message serialization and blah blah blah, right? So I haven't, like, maybe it's different depending on the domain, but I haven't really seen too much use of, like, say, pipes or message queues, or outside of the context of like linking together different utilities. Like if you want to cat the output of some file to like some utility or something, like, yeah, you use a pipe. I haven't really seen it too much in, like, if yours have, say, different daemons running on a system. But
yeah, no, I think that's a good point. Yeah, I mean, pipes would still, pipes and message queue. I mean, the pair Unix message queue probably just works on the same instant of the OS where processes are running in single node. But yeah, but the RabbitMQ and 0MQ that you mentioned, are those? How does that work at high level? I mean, I don't think it's in the context of a embedded system, but I'm just curious. It's still a message queue. So it's like, does it part run as a different server application, or like how does that fit into, let's say a web server has multiple microservices they are communicating? Where does the RabbitMQ and things like that fit in?
Yeah. Yeah, I can talk about maybe, so RabbitMQ, I have not really used it. I'm not super familiar. It is, so these things are used in the embedded context. You will see it especially in IoT systems, right? So for example, instead of like, in IoT, you'll especially see CoAP and MQTT. And MQTT is basically just the RabbitMQ protocol, right? And these are both UDP based, right? But at a high level, you can kind of think of it like, it does a couple of things, I guess. Okay, so the first thing is like zero MQ. Let me just talk about zero MQ first. So zero MQ doesn't have a broker. It's actually just a library, but it's socket based. So it basically looks something like I guess maybe like you have something like the application, and then you have with A, with B, and then there's maybe like a zero MQ context, right? So there is like a generic zero MQ context that is running, and then there is like you link to the context using the library. Yeah, so, and the way zero MQ enables this is that it doesn't have any global variables. Like all the state is encompassed in like the instance of this when you're tying it to the application. So that's one thing. The other thing zero MQ I think does is so it sort of looks like this. You have like a it's been a while since I looked at it, but essentially if you have, say, like if you make like a transport call, it forks off like a worker thread, right? And it'll do something like, I think it's something like the API will, it'll present like a socket API. This is basically just BSC sockets. And it'll fork off like a thread, and it'll create like basically like a session sitting on, this is on your local end. And then it will also have like a listener. So, and then what it does also, I think it maintains these like buffer queues more or less, yeah. So, your API will sort of snoop in on the session and on the listener, and then trigger back to like when you want to make a callback, and like whatever is coming in will be kind of like buffered over inside the local library buffers, and then there's obviously this is going to be all going out to the network. So I think the other thing I know is zero MQ does is that this buffer structure is this is going to be like a lockless queue. So you can do concurrent read and writes. So that is the next thing. And this session manager, it will do a lot of the stuff that we kind of associate with like a broker, like retransmit and session delivery and some other stuff like that. So basically, like on like if you look at like the 0MQ packet that it sends out, it has some metadata basically, and then the rest of this is going to just be like a TCP packet. And then like this session manager will basically snoop in on this metadata and then make some decisions on like routing and all of that. So so that's the basic idea behind 0MQ. Like it doesn't have like a separate broker like daemon that's running, but it does encapsulate a lot of the things that you'd want to see from like a broker. So it's sort of like a trade-off between being like totally lightweight and totally like heavy with like a broker and all. Now another thing I've seen is something like RabbitMQ or Kafka. These are like really a lot bigger. So usually you'll have something like a broker. This is going to do all the things I already mentioned, right? Then broker, you'll have producers that are connecting to the broker, right? And this is going to be over the interface they provide, right? For RabbitMQ, this is MQTT, right? And then over on the other side, you're going to have something like a consumer. And there's different patterns that they support. It could be like different fan out patterns. Like if you want to do a broadcast, it could be like request response, pub sub. Like generally the broker provides interfaces to enable that. So pub sub, request response, broadcast. Like when you set up something like RabbitMQ, like it will, you can kind of set up those patterns. So now the other thing that's pretty common is proxy. So usually it's like not all applications are going to be using this interface. They want to use maybe some REST interface or whatever. So you usually have some type of REST proxy, which gives you like an alternate set of APIs, and then that will just sort of be like a shim that connects to that will do the proper translation for the broker APIs. The other thing I think I see a lot is replication. So usually broker will have some sort of like reliability built in, right? So there'll be like more than one broker sitting on the system. And this could be, and this broker could be sitting in a local context, or it could be sitting in some outside CPU or whatever, right? But generally there'll be some type of replication going on over there. So what would happen is that every time a producer sends a message into the broker, it triggers like a replication event to kind of make a consensus between all the brokers sitting on the system. So, and the last thing I think I've seen is schema. So this is more of like an interface thing. But generally, like if you have a certain schema, right? Like then like the data structure that the broker chooses can change, right? And like you can do some shenanigans, right, to make things faster or whatever. Like for example, if you're let's just say simple schema, message size can only be 40 kilobytes, right? So then the broker, could just set up like a huge pool of just like 40 kilobyte messages, right? And then when it indexes, all it needs to do is just like change a pointer, right? Rather than allocate a new memory or something, right? So it's like tricks like that sort of like will change sort of what data structures a broker will implement. So does it make sense? Does the generic ideas kind of
yeah, I mean, it does. Obviously, I don't have any background on this, so a lot of this is like, but I at least from the concept level, I could make out something from it. But
so I think if you guys are interested in this type of thing, do read up on Kafka. Yeah, so Kafka is a streaming message bus. There's a lot of good material on it, and a lot of the same. Message bus, IPC, RPC, message bus, kind of they're all the same basic thing. It's just like where you've made the trade-offs, right? But the idea is the same, right? You want to get a message over to some other side in a consistent way or reliable way or whatever, right? But yeah, do check out the architecture of Kafka, because there's a lot of good material on Kafka, and it will break down a lot of these, especially around the broker side. A lot of the things that Kafka does specifically. Some of it is not 100% applicable, like because Kafka assumes you have a cluster, and it sets up partitions, and then like producers subscribe to like a topic and some other things like that. But on the broker side, but the idea is like, you want to think about like, how do you do endpoint discovery, right? Or service discovery? Like in the context of like pipes, you just have a file descriptor, right? But if you have a more generic IPC mechanism, you need some way for the producers to register with the consumers, right? So that type of thing.